Hi, it's Ben from Bioremedy. In previous videos, I explained the importance of managing all types of water bodies and how we are so reliant on access to water that is safe and healthy. In this video, we are going to talk about how to manage water bodies in industrial sites. This could be a composting site, a mine site, food processing, or any other on-site wastewater treatment. In video 2, I explain the importance of managing all types of water bodies and how we are so reliant on access to water that is safe and healthy. How we manage a water body is determined by knowing what the determined and future uses of the water are likely to be. There are different water quality objectives for all types of water, as pollutants may differ depending on its usage. The focus on these management options are based around algae and aquatic weed mitigation, odour reduction, and general water quality improvements. Thinking proactively about water management makes the process of maintaining good water quality much simpler, as opposed to reactively trying to resolve issues related to poor water quality. Once the problem can be seen, it requires much more time, effort, money, and resources to return a water body to equilibrium. The strategies explained focus on an industrial process where wastewater is produced. However, similar strategies and procedures are applicable to other types of water bodies, from residential dams, irrigation, water storage, and stormwater retention basins. Firstly, let's analyse the water. Here are some questions that need to be answered to determine our approach for management. What is the size, shape, and depth of the water body? What is the general usage of the water and the potential types of pollutants being captured? Where and how can I have my water analysed to determine its quality and characteristics? What water quality parameters will help me determine my management plan? Now that we have details about the water body, we can now determine what processes are required to improve water quality. Let's look at oxygen. Dissolved oxygen is a measure of free oxygen in water and is often reflective of the water quality. Oxygen is transferred into water through wind and wave action on the surface naturally. When a water body management plan is being developed, the introduction of oxygen is most often the primary process to be established. Oxygen can be introduced artificially through an aeration device such as a Venturi system, mechanical aspirator, surface aerator, or an air blower and diffuser system. An effective way to introduce oxygen is via a mechanical device that produces a micro bubble and deep horizontal flow. This can help maintain aerobic respiration in the sediments on the pond or dam bottom. When oxygen is introduced to this zone, the anaerobic cycle can be broken, beginning the development of aerobic bacteria populations. Aeration device selection is generally determined when considering some key factors about the water body's usage. In wastewater dams, generally the more oxygen being transferred equates to improved results. Higher oxygen transfer rates are produced by subsurface aerators that produce a microbubble. This is not always applicable, particularly in wastewater environments where the bottom sludge accumulates large amounts of toxic metals and gases that can be released if the sediment is disturbed. In cases like this, it is more beneficial to apply surface aeration and minimise any significant disturbance of the bottom sediment. Now let's look at circulation. Often it can be as beneficial as introducing oxygen, particularly when the water depth is greater than 3 metres and the volume exceeds 10 megalitres. At these depths, the water column becomes thermally stratified, meaning that cooler water and low oxygen at the pond bottom is prevalent, and warmer water and higher oxygen levels are at the surface. This is critical in the management of algae in water bodies as it grows in the top 1 metre of water. The introduction of artificial circulation can effectively mix the surface water with the water at the pond bottom, creating consistent temperature and oxygen through the water column. This is beneficial as it breaks the anaerobic cycle in the bottom sediments. Now let's move on to biological treatment. This is the introduction of selected microorganisms that break down organic components of wastewater and greatly improve water quality. If we look at the pie chart in figure 1, This represents the typical makeup of the contaminants in wastewater entering a wastewater treatment system. Of course, the actual percentages vary for different waste streams. The wastewater has three components: an inorganic component, a component that is organic, which is recognized as a food and broken down by microbes, a component that is organic but is not recognized as a food by the microbes indigenous to the system and hence is not broken down in the system. It is this component, along with the organic component of the influent, that either remains in the treatment system as sludge or crust, or exit the system as contaminant in the effluent, which then can become a food source for unwanted plants and algae. Now if we look at figure 2, this implies the changes that could be expected to occur to the relative concentrations of these components following inoculation with microbial cultures. The organic component does not change, but the amount of organic material that is recognised as a food source by the indigenous and added microbes in the system becomes much smaller, and the organic material recognised by the microbes in the system as a food source increases greatly. That is, the added microbes can be expected to recognise more of the available organic material as a food source and break down more of the total organic content in the system than was previously possible by the indigenous microbes alone. This will leave less organic material to accumulate in the system as sludge and reduce the availability as a food source for unwanted algae. Now let's look at chemical treatment. The application of chemicals to alter water quality is common practice in industrial wastewater. Water quality parameters such as pH, alkalinity, suspended solids, total dissolved solids, and biological oxygen demand can all be modified through the introduction of chemicals. The use of algicides, aquatic herbicides, and colorants is an effective way to control many undesired aquatic weeds and algae in wastewater. The most common forms of algae that occur in dams containing wastewater are filamentous and planktonic algae. Both forms contribute to issues related to pumping for reuse and also impact the water chemistry, which can influence other treatment requirements such as disinfection with chlorine. To round things up, I wanted to highlight that management of water bodies is not a one-size-fits-all approach. Each management plan must be looked at with a case-by-case methodology. In our next video, I will discuss in more detail the types of aeration and circulation devices that are suitable for management of water bodies.